So today I wanted to focus on trees, binary trees to be more precise. So I prepared a file with a few exercises. Let me just submit that. Okay, all right, let's get started. Okay, what do we have? So a binary tree is a tree is a very common data structure in computer science. Other data structures that we have are linked lists or arrays, and those are great for linear data. But if our data is more hierarchical, then trees can be very useful. And trees play a big order for heaps and heap sorts, and for they're good if you have to. Hi Ur, thanks for joining. How are you doing? So trees can be very good if you need a data structure where you have to be somewhat fast to look stuff up, find things, but also the data is changing a lot. So say you're an online shop and the inventory and the products come and go all the time. So you always want to be quick displaying the right products to the users, but you also want to be able to add or delete more products as people order or the inventory gets stocked up. All right, so the first thing I want to do is in JavaScript, how we could implement a tree. Since I don't have a whiteboard, it's a little harder to sketch a tree, but we can easily do it in ASCII. So this tree here has a root. The root is always the mother node in the tree, the one that doesn't have any parents. So the root node here has value 6. And then it has 2 children, 4 and 3. In binary trees, every node can have at most 2 children, but there are n-array trees where you can have any number of children. But we'll just look at binary trees today. So the root is 6, has 2 children, 4 and 3, and children are always called the left and the right child. I guess that's pretty obvious. And then 4 again has 2 children, 9 and 1. And since 9 doesn't have any more children, it's considered a leaf of the tree. So if you just think of regular trees, I think leaf and root make a lot of sense. Except when you talk about binary trees, the root is at the top and the leaf is at the bottom. But let's ignore that. And then 3 has only 1 right child. It doesn't have a left child. And one thing we could think of the left child as being null. Like a null node, or just not have a left child here. All right. So let's look how we could represent such a tree in JavaScript. We have a const root, the root, and then, or we have these nodes, and a node needs 3 things. It needs a value, so the root in our case is 6, and then it needs a left and a right child. So if you have an array, you don't have to specify for every element what's the element left and right of it, because that's inherent in the array. But if you have a tree that consists of node, you need to know what the children of the node are. And then if you start with the root, you can traverse the whole tree. If you have this structure for node and you start with this 4, for example, you could traverse the 9 and the 1, but you have no way back to finding the 6. So sometimes trees also have the parent here so that you can more easily walk in all directions. But we can get away with just having the left and the right, and of course the value itself of the node. Okay, so using the structure, we can define our tree. So we have a root where value is 6, and now we can say root that left is another node where value is 4, and root that right is a new node where value is 3. and root that left. Hey Resnode, thanks for joining. Yes, they are recorded. And I also put them on YouTube afterwards so that they don't get deleted after 2 weeks by Twitch. So the left child, so the 4 one, now has another left one where value is 9. Oh, here's a typo. I want value, not variable. And root that left also has a right node. This is a little bit tedious, but we need some example to work with here. And the root that right is itself a node where the value is 3. And now root that right that left, we don't need to fill that out because it's null or undefined. And the right of the right. Hi Anarchy, happy Saturday, how's it going? Which is equal to 8. So this is our whole tree. And if we pass this root to a function now, the function has access to all the nodes in the tree by traversing this tree. And there are different ways to traverse this tree. Pretty good, pretty good. It's finally warming up in New York, so I'm happy about that. It was miserably cold the last days. I mean, not like Chicago, Minnesota cold, but very cold for my personal taste. And now it's above freezing. You can go outside without danger of frostbite or your lungs hurting. So I'm excited about that, and it's nice and sunny at the moment. What are you up to this Saturday? All right, but so there are different ways that we could be traversing this tree. And if you just think about this, one obvious way would be to traverse it the way that we humans read. So we would start at the top left, 6, and then go to the second row, 4, 3, and then go to the last row. And that's one way to traverse this tree. But there's also other ways you could traverse this. You could start with the root, and then you could start over with the left tree and then start over with the right tree. So if we start with the left tree, same order, we're starting with the root, and then we do the left tree and then the right tree. And now for the top root 6, again, we have to, in the same order, do the thing with the right tree. So 3, null, 8. Okay. Another way we could do it is that we first do left, then we do the root, and then we do the right, right? That makes sense. Left, middle, right. So if we do the left first, and then the middle, and then the right. See, the middle is 6, but let's figure out what the left is. So the left is now just the subtree for the top 9, 1. So again, we want to start at the left, then take the middle root, and then do the right. So now the left one, it's just 9, so we can fill that in. This one is just 1, and we have to repeat the same thing on the right. So again, we want to do left, middle, right, or left, parent, right. So the way to do that is the left, and then the parent, and then the right. Now the left is just a null node, and the parent is just 8. Okay. And instead of doing, so what were the ones we were doing? We were doing parent, left, right. We were doing left, parent, right. But we could also do sort of the children first, left, right, and then the parent. So left, right, and then the parent. The parent is 6 here. I'm sorry, that the connection is bad. Do you have the option to select a lower quality? I'm gonna make a note to myself to check the stream quality. I want to play around with this a little more and see, maybe I can get away with streaming in a lower resolution and it's still easy to read. And see if that makes it better. All right, so we were traversing this tree by starting with the children and then reading the parent. So starting with the children, left child, right child, and then the parent. So the parent is the last thing. And now we use the same order to do the left child. So again, we would have left, right, and then the parent, which is a 4. And the left for the 4 is just one node, so we can fill that out, and same for the right. Okay, now we have to do this for the right child. So we want left, right, and then the parent. A parent in this case is 3, and we have null and 8. All right, so there's 4 ways that you can traverse a tree. And conveniently, they all have names, so that when we talk to somebody or when we read documentation that explains how a tree in a certain scenario is traversed, we can just use the name and then both the writer and the reader know what is being referred to. So this first one here is a little different than the other ones. You might have noticed that it's different because it was very easy to write it down. We were just going in order here. And in fact, we were not doing it recursively. This was an iterative approach. And iterative always means that we're doing a breadth first search. I missed out breadth. Width and breadth. How do you spell that? It's not about breathing. Like that. I wrote it down below here. I'm going to cheat and look this up. Nope, I didn't write it down. Well, let's Google it. Depth and breadth. Okay. Yep, so it's a breadth first search, and it's referred to as level order traversal because we're staying in the same levels. So I could do level 1, level 2, level 3, and so on. And it's not a recursive approach, it's an iterative approach. And we're not searching for the depth first, like we're not going all the way to the 9 first. No, we're going in the breadth this way. All right, so whereas the other 3 approaches, they're recursive, so they're depth first search. And in this first one here, we did first a parent and then left and right. So this one is called a pre-order traversal. Then in the next one, we did left child, parent, right child. So that is called in-order traversal. And for the last one, we did left, right, and then the parent, so it's the post-order traversal. And depending what you do, different orders are better than others, like depending whether you search for something or whether you're deleting and things like that. All right, so these are different traversal methods. And we were doing them manually, so let's code that out. Oh, Urs asking, what book is there to read about data structures and algorithm? So one book I can recommend back from when I was in college is this standard one, Algorithms, I think is the name. It has the Calder on the front. Yeah, Intro to Algorithms. It's a very thick and heavy book, but it has a ton of information in it. I don't know if it says how many pages this book has, but it has a lot of pages. Here, 5 pounds. You can hurt people with it if you hit them with it. But that has a lot of information, and it's also going into algorithms that are a tad more complex than your standard ones that you're expected to know during an interview. So for me, that's a good book to read. And then a lot of times the Wikipedia articles are written pretty well, and they usually come with some pseudocode. And I find Geeks for Geeks is also an okay reference. And after that, it just helps to pick a practice problem, try to solve it, and then look up the algorithm on Wikipedia, look it up in some different blog posts, maybe go back to the book and double read that chapter on it, then look at the solutions that other people posted and try to see if you can understand them. Maybe they mention another algorithm and then go and look that up, try to implement that. If you're just reading the Intro to Algorithms book, or like if I would just read the book, I wouldn't be learning the algorithms. A lot of times you have to practice them a few times and try different scenarios until you have this aha moment where it finally clicks. All right, so we have this tree here. What does it look like? Okay, yeah, I can't see much when I print it like this, but we have this tree, and now let's try the different traversals here. So let's do level order traversal first. Well, actually, I wrote them out here, so let's do them in this order, and then compare whether we're getting the right results. Oh, hey Jihati, that extension that prints stuff out, that somebody showed that to me in the last stream, and it's Quokka. Quokka.js. Hold on, I can show you that. Yeah, Quokka.js, and I have it on start on current file. It was only recommended to me last week, so I have the free community version for now. The Pro version has a few more features. Specifically, I've seen, oh no, this works now. Yeah, you just type root, you don't even have to do console log, and it already shows you what all the values are. But I might get the professional version. But I've only tried this since last week, so I wasn't quite sure if I want to keep it. But for stream, it's really useful because you have a small file, so you don't run the risk of anything slowing down, and it can infer everything. Yep, it's pretty nice. I did use it for teaching, though, last week, and the color of the projector wasn't great, and it would put like the numbers after the line. Like I was doing something with variables that all represented numbers, and so Quokka put the numbers here. And so my students who were beginners, they copied from the board, and they would copy this number here that was printed in by Quokka, and of course that was syntax errors. But if you're not a complete beginner, I think it's easy to see, and especially if the colors work out well, then like here it's easy to see this is a different color, and you just know you're not supposed to type this. Yeah, Quokka.js, there's a free version, which is the one I have installed right now. All right, so const in order, it takes a root, and it's supposed to, okay, you wouldn't use it for lecturing. Yeah, then it's not a problem, but if you just wanted to show some stuff or for trying out things yourself, it's a lot more convenient than always switching to the terminal and running the code. All right, so how does in order work? If root is equal to null, then we want to return. Otherwise, do we want to fill an array? I guess we want to, let's just print it out for now. Console.log root.value. So in order would have to start with root.left. Then we want to print the parent, and then we apply in order to root.right. So if we call in order, cannot call left of undefined. So root is equal to undefined. Why don't I see anything here? Oh, and of course I have to call this on root. And then the in-order traversal, so that means left, parent, right, because that's in order, is supposedly 941,638. So what do we have for in order? 941,638. Perfect. Okay, yeah, so we have a recursive function where we recursively apply it to the left, then we print out the parent value, and then we recursively apply it to the right. So we print out in order of this left subtree here, 491, and when we print out that one, we print out 9, and then the parent 4, and then we print out the right subtree. Then we print out those parents, and then we do the same for the right subtree. Yeah, I think they have pretty good integration with frameworks, so they should be able to handle React props, and they can definitely handle imports and requires. Quokka.js. Okay. So this is a recursive function to traverse a tree in order. All right, let's do pre-order. So a function that takes a root node. And pre-order is if we do the parent first and then left and right. So again, if the root is undefined, don't do anything with this node. Maybe it's clearer if we just call this node. Copy and paste problems. Should have just renamed it. Yeah, so if a node is undefined, then return, and otherwise we want to console log the value of the node, and then we're trying pre-order of the left of the node and pre-order of the right of the node. Okay, so if we're doing this pre-order of the root, 649138. Pre-order 649138. Okay. So if you look closely, in-order and pre-order are pretty much the same function. The only thing changing is the order here. So for in-order, we do left, parent, right. And for pre-order, we do parent, left, right. So can you guess what post-order is? So let's write this post-order function, const post-order is a function that takes a node, and if the node is undefined, don't do anything with this node, and otherwise, since we have post-order now, so we're calling recursively this on the children, note that right, and then post, so after we're calling it on the parent, note that value. So post order of the root 914836. 914836 is post order. So in order, pre-order, and post-order, recursive functions are easiest to implement this. And the functions look almost identical. You only have to change the order when you're printing the root value. Okay, so and then the level order traversal, where we do the different levels. Iteratively, we can't use a recursive function anymore. So const level order, we didn't call the other ones traversal either, is a function that starts with the root node. So now this one really takes the root and not just any node, because we're not calling it recursively. So what do we want to do here? We want to have a queue, and if root is equal undefined, then we can't do anything, but otherwise we push into the queue root that value. We push the root into the queue, and then while the queue is not empty, we want to take out the first element, so not the last one added, but the first one that got added to the queue. So constant node is queue.shift, so not pop, because that would give us the last element. We really want the first element. Console log node.value, and now we need to add the left and the right node of that, the left and the right child of node to the queue. So queue.push node.left. I can push two things in one function, right? Okay. So something's missing here. Cannot read value of undefined. Oh yeah, because so now Coca is very nice and everything is red and broken, like alarm broken error. I do check the undefined here, but I should be checking it down here. So I don't want to copy and paste code. So if the node is undefined, I want to continue. And if it was defined, then I'm printing it, and then I'm also looking for its children and I'm adding them to the queue. So 6 at the top, 4, 3, 9, 1, 8. 6 at the top, 4, 3, 9, 1, 8. Yeah, 6, 4, 3, 9, 1, 8. Hi, Temptekine. Yeah, we were just talking about that. So this live output here on the side, that's coming from Quokka.js. I'm using the free community version at the moment. I just learned about this plugin last week at the stream, so I'm still evaluating before I buy it, but it seems very useful, as I don't have to like switch over to the terminal and be like Node trees.js to see anything. Let's commit this traversal methods. Yeah, I found it pretty useful when somebody told me about it. All right, so we covered a few of the basics. Trees are good data structures if you have hierarchical data. I hate this word. They're really useful for a lot of the questions in programming whiteboarding interviews, so you definitely need to know them. The structure of a tree is actually really simple to implement in JavaScript. Nodes just need 3 properties of value and a left and a right child. And then left and right children will be nodes again. So here we have a little sample tree, which looks like the one that I drew up here. And then there's different ways to traverse a tree. There's in-order, pre-order, and post-order. Those are recursive ways to traverse it. And then there's the iterative level order traversal. So we just quickly implemented all of those. And I've prepared a few questions that I thought sounded good, and I want to try implementing them now. All right, so first question. Given in-order and post-order traversal of a tree, construct the binary tree. All right, So we're given in order and post order, and we're supposed to construct a tree. Here's an example. And how would we construct a tree? Like, how would we check that we have the right tree? Would we give it a level order traversal? Oh no, we would like set what the root is and then go from there. All right. So in order and post order, they look different because we are traversing the same tree but in different orders. And one thing for in order, you don't know what the parent is, because if your tree is not balanced, if your left-hand side is much bigger than the right-hand side, then the root parent will not be in the middle of that in order array. But with post order, so for post order, we know it's left child, right child, parent. So we can definitely say that this very last one here is the root of our whole tree. And since we're also given in order, so we know 3 is the root. Let's just draw this out. So we know 3 is the root. ASCII art. So by looking just at the post order, we now can't say anything, because from these 4 numbers, we don't know which one of them belong to the left and which one belong to the right child. Like, it might be that the right half of the tree is null and that they all belong to the left, or that it's 2 and 2. But that's why we were given in order. So the 3 is here, and we know this is in order, so we know the 9 is the left and the 15, 27 is the right. So the 9 is the left here, and the 15, 20, and 7 is the right. Again, we don't know this is in order, but we don't know which one of those is the root. But if we look at this one here, we know this is the left, and this is the right in order. So from that one, we know that 20 must be the parent, because it's the rightmost one in post order. And then if 20 is the parent, then we know if 20 is the parent here, then we know 15 is on the left and 7 is on the right. So 15 goes to the left. Oh, it's so hard to write ASCII, and 7 is on the right here. All right, so this is what this tree represents. And now we need to write a function that does exactly that for us. So const make tree is a function that takes an in order array and a post order array, and it should return a root, which then links to all the other ones. So if in order that length is equal to 0, then return an empty tree. And otherwise, const root is a node where the is a node, and let value is equal to post order. Now we want to get the last one. All right. So root has the value. Now we need to find the left and the right child of the root. And I feel like we have to make an iterative function here. But so once we have the root, we want to return the root. And we want to say root that left is the same make tree function, but now with a different in order and post order. Make tree. Okay, So now that we have the value, so we know the parent value is 3, and then when we were talking about this, we figured out that the 3 has this position here, so we knew we were separating at 9 and 1527. So that's the next information we need to use. So let index equal Inorder that index of value. So that was give us index 1. And now we want to, how do we split those up? Yeah, we need to do a bunch of array splitting. And I quickly need to check, I can remember that. So let A be the array and A that slice 2, 3. Does that give me 0, 1, 2? Does that give me 8? No, it gives me 6. So because it's 2 is the 0, 1, 2, 2 is the first index, and 3 is the ending index. So we're going from beginning to ending index, and it doesn't change the array. All right, so we want to make a tree now where we take Inorder that slice, and we're going from 0 to index exclusively, and we want the post order. Yeah, what's the post order? Post order is going from 0 also to the index, because that tells us how big it is. Post order that slice from 0 to index, and root.write is also recursively calling make tree. And how are we slicing? Okay, so -1 is cutting off the last element. I think that's what we want. So we want to start from index +1, because everything on the right. Oh, and then just to the end, right? Yep, okay. To the end, and for post order, we want to start at index, which would be the 15 now, and we need to cut off the end. How does that look? So if Inorder is equal to 0, return null. We take the last element, last entry, because that's the parent. And then we search for the parent in the Inorder one. And that tells us how much we have to slice the Inorder for the left search and for the right search. Yeah, because we slice the left and the right. And we're leaving out index. And for the post order one, we use the same index from 0 to this index. And then, okay. So we want make tree, and we need these two indices, so in order and post order. Okay. What does that look like? So sometimes this plugin doesn't seem to work. I'm not really sure. Oh yeah, because we were reusing the same variables. So let's use the Inorder input and the Postorder input. Postorder is not a function. So let's get rid of all of this. It's still complaining Postorder is not a function. Well, I'm not trying to use it as a function. Or actually, we could just use Inorder and Postorder inputs here. All right. So what's happening here? Line 89. 98. I forgot a slice. Thank you, WebMac. Hi, Ditiran. Thanks for watching. Thanks for helping me debug this. All right, now it's green. This is hard to read, so I guess we will have to switch to the console. And where's the initial tree? We start with a 3. Then we have a 9 on the left that doesn't have any children. And we have a 20 on the right that has a 15 and a 7. Awesome. Okay. Yeah. And there's some rules about if you have Postorder and Inorder, you can uniquely determine a tree, but it doesn't work if you have other combinations. Determine tree from post and pre-order. Like, I think this does not work. Oh, here you have full trees. Yeah, it's not possible to construct a general binary tree from pre-order and post-order traversals. So if you're given 2 traversal sequences, can you construct a binary tree? It depends on what traversal sequences are given. If one of them is in order, then the tree can be constructed, otherwise not. So if you don't have the in order, you can't construct it. So if you have in order and pre-order, or in order and post-order, but not if you have post and pre. Yeah, for example, pre-order, level order, or post-order traversals are the same for the trees given in above by diagram. Oh yeah, because AB and AB, left and right, you can't really determine that. Okay, but as long as you have in order as one of them, you can construct uniquely the tree. So that's what we just did here. What am I doing with trees? Oh, I'm just solving interview questions. And I talked a little bit in general about trees, and now I'm just solving a few problems that I found on different interview websites. So the first one was this one here. If you're given in order and post order, construct a binary tree. So we just did that with a recursive makeTree function. All right. So let's commit that. Construct tree from in order and post order. All right. Next problem. Given in order and post order traversal of a tree. No, we just solved that. What am I talking about? Weird. Okay. This is literally what we just solved, right? All right. Now the next problem. Oh, okay. Given a singly linked list, single links, where elements are sorted in ascending order, so So no, I'm not applying experience from tutorials. What am I? Where did I get my knowledge from? I had a few CS courses. I was a math major many years ago in university, and computer science was my minor. So we did a little bit of theoretical computer science and talked about trees and algorithms and complexity. I was just showing somebody else. I like this book. It has a ton of information, but it's good for references. And then what I usually do is I pick a problem, I try to solve it, I read up the algorithm on Wikipedia or Geeks for Geeks or maybe some blog posts, whatever is ranked highly in Google search. I try to solve it and I read up a little more, and then I look at the other solutions and maybe somebody mentions another algorithm. That's kind of how I study those. Yeah. And I just have fun solving this, and it's fun to do it on stream where people can give me, maybe you can like pair program or mob program. Like last week somebody suggested this really cool plugin, Quokka.js, so you see the output right here and you don't have to switch to the console every time you want to console log something. I like that. Yeah. And if you have any data structures and algorithms topics for interviews that you'd like to see covered, let me know and maybe I can make a stream on it. It's the Geeks for Geeks. Geeks for Geeks. Sometimes the way they're written, like the language itself, is not necessarily the most clear language. I think it's a lot of people who are non-native English speakers who contribute, but I find that they are extremely correct and fairly precise. Like it's still a good resource, even though sometimes I'm like, oh, that's not really an English sentence. But they're still easy to understand. They have good examples. They always have a little bit of code. And I don't know if they're edited or community edited, but I've never seen them being off. Like it's never that they're like, oh, linear complexity, and you're like, no, that's quadratic. Like they're pretty good. Oh. Yeah, I really like watching other people, watching other people stream as well, because you're like, oh, that's a cool shortcut, or that's a really nice new syntax in ES6, so that's a cool algorithm. And I only started streaming recently, so I haven't fully figured out what works well on stream and what doesn't. If you have any feedback, let me know. Still learning. What I like about interview questions is that they usually fit on the screen. So even if you jump in late or if you missed a few minutes, you can see all the code and follow along. Some streamers, when they stream big, complex projects, I always feel a little lost because obviously it's on their machine, so I cannot just look at the other code and scroll, and I'm like, I don't know what they're doing. All right, so next problem here. Yeah, so this one here was kind of a warm-up problem. I thought I had another good warm-up problem. Maybe not. Maybe this one's still a warm-up problem. So, given a singly linked list where elements are sorted in ascending order, converted to a height balance BST. So, BST is a binary search tree. So if it's a binary search tree means that everything on the left on the parent is less than and anything on the right is larger than the parent. So it's easy to sort. Oh, you rewatch and rewind. Yeah. Yeah, I mean, there's different ways to watch them. Some I have kind of on as background streams. Some videos I have on to actually learn it, in which case I rewind and I pause and I fast forward and I rewind again. But there's different ways of how they're good. Yeah, and I always share my code on GitHub. So it's right here. It's github.com/fhinkel, and the repo is called Twitch. So if somebody is watching the recording, no, so left is less and right is greater. Yeah. All right. So we're given elements and we're supposed to convert them to a tree and to a binary search tree. And a height-balanced binary tree is defined as a binary tree in which the depth of the two subtrees of every node never differ by more than 1. All right. Okay, yeah, so we cannot just turn this, we could turn this into a valid BST by just starting, yeah, we could start on the left, and then we could just go down to the right. This is actually very easy if we ignore that condition that it has to be height balanced. It's not necessarily a pretty tree, but it's a valid binary tree. You see what I'm trying to do here? So this is a valid binary search tree, except it is obviously not balanced at all because the left side is 0 and the right hand side is 1, 2, 3, 4, 5. Height has height 5. Yeah, but so this is a valid tree because the right child is always larger than the parent, and the left child, which doesn't exist anywhere here, but if it, like, the condition for the left child is it has to be less than the parent. Since we don't have any left childs, we're not violating this condition. So this is a valid BST, except it is not height balanced. So for it to be height balanced, it should look something like 0 would be in the middle. Yeah, before I code it, I kind of want to understand it in my head, so I have to draw them out. And since I don't have any cool setup where you can see my pencil and paper, I have to draw them on screen. And I find it hard to reason if I solve the tree problem correctly if I don't have a little drawing anywhere on the board. So if we turn this example here into a height-balanced binary tree, then we would turn it into 0. Am I doing this right? -3, 5. And then on the left here, here it's on the right. Okay, so this is also a correct BST. Where are trees used in the real world? So for any heap structure, you need a tree, and then heaps are used in heap sort and lots of other data structures where you need both quick access, but also quick insertion and deletion. Yeah, you can have a balanced trees, like red-black trees, and then your height is always log n. So searching anything takes at most log n, and insertion and deletion with the rebalancing also takes asymptotically log n, so you have a pretty fast algorithm. All right, so let's read this again. Is a binary tree in which the depth of the two subtrees at every node never differ by more than 1. So is this a correct height balanced tree now? I'm wondering because I think there's more options here, right? I mean, this one has subtrees 0 and 1 height. This one has subtrees both of height 2. Oh, thank you. But isn't there more than one option to write this? Like, what if we were to start with -3? Obviously, -10 needs to be on the left. And then -3, 5. We would have the 5 here. and the 0 here. Isn't this also, is this a BST? Is that correct? Oh no, it's not correct, because now the 0, even though it's less than the 5, the 0 is, no, 0 is more than -3, so that's okay. Is this height balanced? Yeah, I'm confused how to do this correct in a unique way. Convert it to a height-balanced BST. For this problem, a height-balanced tree is defined as a binary tree in which the depth of the two subtrees for every node never differ by more than 1. So which one of these two would be correct? This one has depth 1 and this one has depth 2, so that's fine. Like, I feel that this one is more balanced, but maybe it's not. And I think the other option to write this is, maybe that's what we need to do. Maybe height balanced also means filled up from the left. So if we start with a 5 here, and then, okay. Can everybody double check me? Is this here, is this really a BST? I'd say it is, right? Everything on the right is bigger, and then for every node, again, it's smaller. So another way you could write this is -10. Like this, right? 5 is less than 9, 5 is bigger than everything here. -3 is less than 5. And then -10 and 0. It is, all right. Thank you, MSS, AlexX, and hi, VindicativeF. We're looking at binary search trees. And the problem is, if you're given a singly linked list of elements that are already sorted, you're supposed to convert it to a height-balanced BST. And then it says for height-balanced BST is a binary tree in which the depth of the two subtrees for every node never differ by more than 1. And I'm just confused because if I'm given these numbers, there's multiple height-balanced BSTs that I can write. So I'm not quite sure which one I should write. Because these are still height-balanced, I thought. Where heap sorts used in the real world? I think they're part of quite a lot of sorts. Like, it always depends what predictions you can make about the data and what your other constraints are. So where's the heap data structure used? Oh yeah, lots of graph algorithms use that, yeah. Like Dijkstra uses a heap for doing statistics. Oh, and they claim the Linux kernel uses heap sort. Oh, a heap sorts are used as backup for quicksort if quicksort goes too deep. What do you mean with going too deep? All right, so since I'm not quite sure which one we're supposed to use here, I mean, there's lots of sorting going on, like for process scheduling or for the file system, like lots of ways where you could need to sort. So since I'm not exactly sure what the correct answer here would be, because just looking at this example, I find multiple height balanced BSTs. So we'll go to where I got this example from, which was from LeetCode, and solve it in there, because then we have lots of test cases, so we can hopefully figure out what's missing. Sign in. Sign in. No, I'm going to sign in with Google. All right, and we want a tree. And we're looking convert sorted list to binary search tree, right? That was the problem we're solving. Oh, okay, so MSLLX says quicksort has worst case n squared. If the recursion goes too far, some common sorting problems use heap sort as backup. Okay. I thought all the real sorting algorithms are a combination or modification of these basic algorithms. Like I thought a standard quicksort doesn't perform as good as lots of other sort variations. Like I know V8 uses a TIM sort. It doesn't use a straight up quicksort or merge sort. It's like a fairly new algorithm. But yeah, the underlying basis heaps are used quite a bit. Heaps and trees. Yeah, so this is the problem. Oh, okay, so they are saying one possible answer is 0, minus 3, 9, minus 10, 5. Oh, did I do that wrong? 0, minus 3. Oh, so what they did here, they had, instead of having it like this, they say one possible answer is put the 9 here, and then the 5, of course, has to go to the left of it. Okay, yeah, so there's lots of options here. One possible answer is 0, minus 3, 9, minus 10, null 5, which represents the following height BST. Well, I guess we'll solve it here and see what to do if there's more than one solution. Okay, yeah, so C++ stdlib is using quicksort and insertion and heap sort combination. Yeah. Yeah, and I think for very small data sets, like an insertion or selection sort is usually kind of quick. All right, so how do we want to solve this? Yep, JavaScript's the right language here. What's the difference? Oh, that's the list and that's the tree. So we're given this list which has a value and a next, and then we want to write this out. So the first thing we could do is const input, and then while head, we want to say input.push head.value and increment head by 1. So now we have all the numbers in inputs, and now let middle equal, I think we could always just take the middle element and then apply this recursively to the left or the right. So let middle equal input.length divided by 2, and we need to use whole numbers. So let's take the middle, and then we want to say const root root that value equals input of middle index. And root that left I'm glad this is helpful. Yeah, so what do we want to do here? So we have the root value, and now we need a left and a right one, and I have a feeling we have to do this recursively again on like an array.slice. So here we could take input that slice from 0 to middle index, and here we could, sorry, this is the okay, let's put this part here in a recursive function. So var recursion, and it takes an input array, and what it's supposed to do is this here. So the middle index is method flow of input at length divided by 2. The root node is a node where the value is this, and then left and right, again a recursively calling, and one takes this input and one takes this input, and we need to return a root so that we have a node object that we're returning. Since this is recursive and not only called on the real root, I'm going to use node here. So constant node is a node where value is the middle one, and then the left and the right one are recursively the nodes when we are slicing in the middle again and we're returning the node. So down here we want to say the root is equal to recursion of this input that we just generated. And I guess, are we supposed to return the tree? What's this function supposed to do? These are the definitions. It returns a tree node, so it's supposed to return the root node. So we can, okay. Oh yeah, thank you so much. Copy and paste arrow. So we want to slice from the index, but exclude the index all the way to the end. Does that look right now? Okay. So how is this going to solve the problem that there's more than one option here? Let's see if this even runs. No, it doesn't run. Because this is not valid JavaScript function recursion. And this is not valid JavaScript. Can I like format this code? Settings, shortcuts. Is there anything like format? No. Huh, I miss my editor. All right, cost size exceeded. Yes. Anybody see? Yeah. Thanks, Vindicative F. I'm so excited that you're watching. The stream wouldn't be fun for me if nobody's watching, and I'm getting a lot of useful input from chat too, so I really like that. All right, so we're getting a caustic exceeded because we're running into this infinite recursion loop. And what's missing here is that if input.length is 0, then we need to return null or undefined. And only if it's not 0, then we take the number and we do recursion on the left and on the right. This might also be broken, right? Because what happens if you slice an array that's bigger than what you have? So a that slice, what if we start slicing at 7? Oh no, that's not too bad. Is that bad if we do this? No, we would just call this on the empty array, which isn't a problem. And if we just have one element in there, 1 divided by 2 is 0.5. We take the floor, so it's 0, so this one here will still work. Length on line 20 has a typo. Thank you so much. This is I hate this word. I don't know why it's hard to type, because I know how to type it. And when you say length, you hear that th at the end. Alrighty, that worked. Wait, it said finished, but my output is 0, -3, 9, -10, null 5. And they're expecting something different here. Okay, what happened? Why are they expecting something different in my output? So 0 is the root. We get that correct. Whew, good. And then I continue with -3, whereas they continue with a -10. If I continue with a -3, isn't that... So I'm confused here because the input is the same input as in this example. And they even say one possible answer. So they even say one possible answer is the one that I just printed out, which represents the following height balanced tree, but the expected answer is different. Yeah, there are many possible solutions. So why is this why is the expected one not the one they have in the example? I'm gonna cheat here. Okay, height balanced, yes. The middle element is the root. Left subtree, okay. That makes sense. What are people saying? Oh yeah, JavaScript's good. Oh, are they maybe printing it out in a different way? So 0, that means we're doing pre-order. I don't even know what order this is supposed to be. Like this one here is level order. But what is this one? And why is nobody else struggling with this? Okay, you're saying submit your okay, I guess we can always try that, but it wasn't even, wait, that worked? I'm so confused now. How is that correct if like the example didn't work? Do they check if it's any possible tree? I'm confused by how this question is asked. But it's a success, so I'm happy with that. Okay, thank you, Mindful Fox. I had no idea that they check against all of them. I thought they might assume that you have to like make it everything on the left or like always take the middle or something. Oh, but they only show one. Okay, gotcha. All right, cool. So we solved this one. We still have some time left. So, yeah, we solved this one. Solution. It's on the internet. Just use that one. All right, so I think this one is a fun one. I haven't solved this one yet, but it's not a warm-up problem like these other one. Oh my God, congratulations. Which office, Mindful Fox? I'm in a New York office. We all came to an agreement that the New York office has the best food options of all the offices. Well, like all the 10 or so offices that I've visited so far. Well, big congratulations. So you passed the interviews, you got the offer, and you're still watching streams about trees and heaps. Nice. Oh, cool. I just got a new Pixel 3. I still need a case because I'm super clumsy, and without a case, this will not survive very long. Cool. Well, big congratulations. You should start your own stream now. How to interview at Google. Okay. Oh, the space race. You know, I have no idea. We're doing so many things at Google, I cannot keep track of all of them. So if you read the news, you probably know just as much or even more than I do. Okay, why did they copy this? You know what? There's Git for a reason. No, I don't want to delete everything because then later it's gone, but we can. We can move this question to the beginning, so I have the tree right here. All right, isn't the weather really bad on Mars? I don't know if I would want to move to Mars. Oh wow, there's a horse on the street. I'm in downtown Manhattan and somebody is just walking their horse down the street. That's wild. Okay. Okay, given a binary tree, so we're given a binary tree here by this root number. Find the maximum possible sum from one leaf node to another. So const maxsum is a function that takes a root and it's supposed to return something. Let's define this right here. Okay. So, what's the maximum sum for this tree? Yes, you do casually walk the horse. I mean, what else would you do if you're in Manhattan? Of course, you like have a horse that you walk down on like 10th Avenue. All right. So for this tree here, it's pretty straightforward. We just have to pick the two largest numbers for the leaves here. And that would be 9 plus 4 plus 6 plus 3 plus 8. It would be a different question if we had a -3 and a -9 here, right? Because then 1, 4, and 6 is 11. But 6... Yeah, while you get your groceries. What if somebody steals the horse, though, while you get your groceries? Then how would you get home with your groceries? Yeah, so if we have this made-up tree here, now the biggest one... Oh, and it has to go from 2 leaves, so we cannot do 1, 4, and 6, because we always have to take leaves with it. But the biggest one would probably be -9 plus 4 plus 1, which is -4, because here with the -3, anything gets much smaller. So we would do 8 minus 23 is -15, plus 6 is -9, plus 4 plus 1, and they're also 4. Maybe these numbers are not the best numbers. All right. Yeah, so we want to take the leaves. So we cannot stop at this or this node. It has to be a leaf. The tree is not a search tree. It's not balanced or anything. So it's just numbers. They can be positive or negative. And we want to find the maximum sum. All right. Let maximum equals numbers third negative infinity, because we want to find the maximum. And we're starting with the root. So we want to find, how do we do this? It has to be recursively because we have to go down everywhere. And we want the sum. Okay, yeah, so I think for every node, we want the sum going through that node. Yeah. Oh, and the root does not need to be in this maximum sum. Like, this little subtree here might have the maximum sum, or maybe it's the whole thing going through the root, but the root does not necessarily have to be in that one. So we want to have the maximum sum of the left tree, the maximum sum of the right tree, and the maximum sum going through the parent. All right. So if root is equal to undefined, then I guess we're just returning the maximum because nothing's changing. Okay, so I want this, so if this is our root and it's a leaf, from one leaf to another, so if it's just one leaf, that doesn't help us. Yeah, I might need a helper function. I was thinking I could call this max sum function, but probably not. So what do I want to do? I probably want to have the left sum and the right sum, and then the maximum of the two of them. So, and what sum do I want? I want this largest sum going from any leaf, including that node or up to that node. Okay, I want the largest sum up to that node on the left and on the right. And if I have a left and a right, then I can set the maximum to the largest sum on the left plus the largest sum on the right plus the root and compare that maximum to the other maximum I had. So const sum until node, it takes a node and it takes a current max result, yeah, current maximum, and it's a function. All right. And the sum until node is Postorder Traversal. Sounds good. This, and then the node. Yeah, that sounds right. So if node that left is undefined and node that right is undefined, then we're looking at a leaf, right? So the sum until this node is a leaf. Not sure what we're doing if we're looking at the leaf. If node.left is defined and node.right is defined, so it has left and right, so somewhere left and right will end in a leaf, then we can return sum until node.left plus sum until node.right. Hi, Ping Horse. Were you the horse that just walked by on the street here? No, I'm not using TypeScript. I'm using TypeScript for real projects, but for these small projects, just solving little interview questions, I don't need that. So I have the left node and I have the right node. Don't have this, I'm returning this. I see copy and paste errors happening. I'm sure they're happening. Oh, that was your brother. Okay. How does he like the cold weather? How does he like living in New York? I feel like that's not really a horse place. And also, what kind of occupation has your brother that he can afford being a horse in New York City? I'm sorry, I was just confused. I was like, I have this big window here, and sort of like I glanced out while I looked at the screen, and all of a sudden, there's just somebody walking down the horse. No, it isn't even on the bike lane or anything, so I don't know. Okay. So if we have a leaf, then I guess the sum is just note that value. And if we have a left and a right node, I'm pretty sure we have to update the current max. Should I return an array of node and current max? Oh, I can just pass in an object with the maximum. Current max is like this. And then I can say current max stat value is math, stat maximum. And so current max. I wish there were an operator that just like plus equals, there should be like a max equals, because for interview questions, I'm using it all the time. So it should be the current max, or isn't this the new leaf value? Yeah, I think that's the new leaf value. It's the sum from the left node plus the sum from the right node plus the current value. That's the current max. Except, yeah, only if I have left and right, then those will have a node. And if I don't have a left node, this is not quite right. This is not quite right. So because here I'm going either 146 minus 25.8, or I'm going, yeah, let's make this a little simpler. So if this is our tree, then the sum is 1 plus 4 plus 6 plus 7, and it's not minus 9 plus 4 plus 6 plus 7. So the sum up to node 4 is minus 9 or 1. It's minus 9 or 1. So the sum until node 4 is minus 9 plus 4 plus 1, but the maximum is, what's the current maximum if you just have a leaf? If you just have a leaf, then it stays at minus infinity. So the next maximum is from minus 1, yep, that's the left node, plus the right node plus that. So it's this whole thing. And then the sum up to 4 is minus 9. I think this one here is not right? I want to say math.maximum. And I'm either taking the left or the right one. Does that make sense? Am I missing something here? So if we don't have a left node and we don't have a right node, then we have a leaf. So the sum until this leaf is 0. No, it's the value. Am I using any built-in functions? Well, I'm using things like math.max, which are built in. And if I have a left and a right node, then I will change the current max if it is better than the previous max. And the current max now is the sum of the left plus the sum of the right plus that node, because I'm going from leaf to leaf. And the sum until node, so this really is like the best sum, let's call it max sum until node. And the maximum sum is always the maximum of either the left or the right plus that value. I think I like that. Are you guaranteed 2 leaf nodes? No, I am not. I am not. But the tree, well, I guess we can, no, we should check that. If the root doesn't have a left or a right, okay. Yeah, this is something we could do. So if not root return number that, then we don't have this. If we don't have a root, or if we don't have a root that left, or if we don't have a root that right. So I know my root has at least, does have 2 leaf nodes because it has a left and a right node, so somewhere they will end up in leaf nodes. But I'm not guaranteed 2 leaves on every node. That's why I'm checking here if I don't have a left one, or if I don't have a right one. And I really don't like how I all of a sudden use the shortcuts here. I think I'm just gonna use shortcuts everywhere. If we don't have a left node, and if we don't have a right node, just using the value. What if we are, yeah, the important part missing is if we don't have a node. Then the sum, so we're trying to go down there and there is no sum. We're adding it up. So I guess I have to return 0. Yeah, I think that looks right. So the maximum is that. And then I want to say max sum until node of root and maximum, and then return max.value. How does this look? Oh, that's too big for one screen. Okay. So if we don't have a root, or if the root doesn't have a left and a right child, then we can't find any distance, so negative infinity. Maximum is equal to minus infinity for now. Then we're calling maxsum until node from the root, pass in the maximum, and then print out max.value. And maxsum until root, if the node doesn't exist, it returns 0. If it doesn't have a left and it doesn't have a right, so neither one of them, so that node exists, so the maximum sum up to that root is the value of that one. If it has a left and a right one, then potentially we can update the maximum by taking the current maximum is going the max sum of the left plus the max sum on the right plus the current value. And then we will return the bigger and better one of either the left or the right plus the current value. And I'm doing this computation here twice. I don't like this. So const max left is this one. And const max right should save some complexity. If we don't have a left node, then we're summing up the right nodes and add the value. We can't change the maximum because without a left node, we are not having two leaves right now. Okay. So what kind of tree should we use? We should probably use this initial tree. It was 4 and 3, and left was a 9 and 1, and the right, why do I have right twice? Is that the tree we had? Six, 4, 3, 9, 1, 8. I think that was the tree we had. So what's the maximum here? The maximum we're expecting is 9 plus 4, 13 is 19, is 22, is 30. Let's see if that's equal to 30. Max sum of tree. Don't have a tree. Oh, root. Root. Okay, that's a property value of undefined. Max left is max sum until note that left. Oh, I see. I'm never passing in that current max. So when I'm calling max sum, of course it needs 2 parameters. And this is not read because I don't even have that case. Oh, and it would be good if I'm using the correct function name. Console log. No, it's not a number. Bummer. Yeah, the current max was missing. All right. So max.value. What's going on here? We don't have a node, not that value. Console.log current max.value. So we're going from infinity to not a number. So what are we doing wrong here? At some point we're adding something to it. So we get to this one here. And we say current max is the maximum of current max and left, right, and node.value. That looks very much like a number. That looks like a number. That looks like a number. So what's the problem with current max and left, right, and node.value? So we want the current maximum. Was there maybe an no, it would print undefined if it were undefined. Math.max. Does math.max take an array? No, it just takes values, right? So that didn't work. Oh, I see it. All right, that was silly. That was a lot of debugging for not seeing that. Okay. Yep, and the current maximum is 30. Cool. All right. Okay, so that was almost a 2-hour stream, so I think I had enough. Let me clean this up. I don't like this. Should we do another test case, because we just had a test case with all positive numbers, so that's probably not the best test case. Do you want to help me make a better test case? What's a good one? Or should we just assume it's right because it works on this one test? I guess we can add some minus signs here. So if the 9 is negative, so if this is negative, then what do we expect the maximum to be? Then the maximum should be this path here, right? 1, 4, 11, 14, 22. Yes, okay. And if this one has another leaf that's really big, then it's better to take this whole route again. So it's 21 minus 9 is 12, 112. Oh, I need to add that here though. I need root that left has value 100. Yeah, 112. Cool. All right. So compute, what are we doing? Compute maximum sum between leaves. Cool. Thanks so much for watching, everybody. Hope this was interesting. I remember when I first practiced for the interviews, I did not like trees, and when I would see a tree problem, I would be like, oh my gosh, I can't implement a tree in 45 minutes. How am I even supposed to do that?